get started. So today we're going to talk about a very important topic. Alright, so we're going to introduce this issue called endogeneity, and then we're going to introduce a method to account for that. This is called instrumental variables. Have you heard about that? We oftentimes refer to it simply as ID. Alright, so this is the ID approach. It's a commonly used approach to address this endogeneity issue. So that after addressing this endogeneity issue, we are more confident to provide the so-called causal inference. Alright, so this is a part of this causal analysis. So, yeah, for those of you who have never heard of that, have never had any idea about this potential issue, pay close attention to that. Okay, and then you may need to read the corresponding book chapter carefully, to get a better sense of what the issue is and how to account for this problem. Now we start this time, we've talked about all those nonlinear models, right? So we started with the linear regression, we talk about what if the dependent variable is limited. It can only take binary values, it's truncated censored, it takes count values, it has the duration, the time duration, right? And then last time we talked about the discrete choice model. So the dependent variable is still discrete, but it takes one value out of multiple options, right? So those are all extensions starting from this linear regression model, and then we talk about all those different nonlinear models. The last topic, this is the last topic of our first module, right? So this econometric and statistical model, the first one. So in the last topic, we're gonna go back, okay, to the original starting point, this linear regression. But we're gonna talk about a more profound issue of linear regression. So we go back to this linear regression, right? That's the basic linear regression setting. Right now, everything goes back to normal, the simplest setting. Y is you can take any value, X can take any value, we just consider it a linear regression. But now, the simplest thing sometimes is the trickiest. Right? So go back to this linear regression, think about that. What is one of the key assumptions that we have imposed in standard linear regression? And so I mentioned that in the first topic where we discussed that. Yeah, this one. Linear regression, we have this error term, right? So y is it's determined by a combination of all those x variables plus an unobserved error term. Error term is modeled as random variable, right? Then what's the assumption that we have imposed for the distribution of this error term? This one. This is the key assumption. Expected value of that error term given. You see, this pipe is given, right? So some of you ask, what does this notation mean? The pipe is given conditional on, okay? Given conditional on any value of all those x variables. The expected value of this error term is always 0. All right, actually I explained. Think about that. What is that? Essentially, what does this assumption mean? Roughly speaking, you can think of this assumption as talking about the error term's distribution is independent from the values of those x variables. All right? Because it says no matter what x values, given any x values, the expected value of this error term is always 0. Right? So x value could be high. For a high x value, expected value of the error term is 0. For a low x value could be low for some observation. But even for an observation with very low x value, still the expected value of the error term doesn't change. It's also increased. So essentially, you can roughly think about, but although it's not exactly right? So this is the precise assumption that we have imposed. So it's weaker than what I just said. The distribution is independent from that. It's weaker, but roughly you can think of this way. Essentially, we are assuming that the distribution of the error term is independent from the values of the x variables.
Can you also say you're assuming that the errors will basically cancel each other out if they're mean 0?
No, it's not canceling each other. Each error term is independent. Each UI is independent across individual I's. All right, so that, yeah, there's it doesn't, no need to cancel each other out. So it's more like this is a random variable. Each UI is a random variable by itself, right? So take any random, any value and follow a certain distribution. So what we are assuming is that this distribution is centered at 0. Remember, I explained that actually this 0 itself, this value per se, is not really a strong assumption because it's just a normalization. Right? What's really a strong assumption is that the expected value of the error term is always equal to a constant, no matter what value the x variables take. So this actually could be a very strong assumption. Why? Think about that. Let's look at this example. Let's look at this example. It's easy for you to understand. Let's say we talk about this, this simple analysis. We want to investigate the so-called return on education, right? So use, different people spend different lengths of time in school, right? The years, different years of schooling, different to receive different level of education. And then, we can collect the data about their earning capability, right? So eventually, what is their wage, say hourly wage or, whatever wage, monthly salary, right? We can calculate that. And then we calculate data for a lot of people, right? So we collect the data for a lot of people. Then we can estimate, say, the return on education, right? So say 1 additional year of schooling, right? How much will that increase or maybe decrease, right? The earning capability, right? We can calculate that. So we can run a simple regression, if we have the data, right? To regress wage on years of education, and we can estimate this coefficient beta, right? As we said, what does beta measure? The marginal effect, right? So 1 additional year of schooling, of education, how much will that increase the expected hourly wage for that, right? So let's say if that's the only data we have. Of course, we can collect other data, right? So other like demographic, all those like observable data, and then we can store that into regression as control variables. But let's say if we only observe this, all right? So let's just forget about the rest. Yeah, let me now show you that. So only about this education. We regress wage on education, and then we run a regression. What could be the potential problem? According to the basic regression setting, what is the assumption? Error term is independent from this x variable. Right here, the key x variable we are interested in is this education, years of education. So what the basic linear regression assumes is that the error term's distribution has nothing to do with the value of that x variable, that years of education. Now, do you think, is that true? What could be wrong? What argument could you come up with to counter that assumption?
There are other factors that you're not considering right now that education could affect and.
Exactly. Think about it. What is the error term? What did we say is the is containing the error term?
Missing information.
Yeah, everything that could affect the y variable, the outcome variable, but is not included in the x variables that you observe. All of them enter the error term, right? So including the missing information, including the what we call the omitted variable. There are a lot of variables that you do not observe, right? But if they affect what? Affect the outcome, in our case is the wage, and then they enter the error term. Now think about what could be those omitted variables. What could affect a person's wage?
Where they're living or which country they're in.
Yeah, which country, but that's, you can observe, right? Those are the data you can observe, you can collect, you can control. Something it's hard to observe, but it will affect the wage, affect the error.
This example would be ability.
Exactly, excellent, right? So innate ability, someone's, ability. So if they are a capable person, yeah, it's likely for them to be able to find a better job with a higher paying job, right? But it's hard to observe. It's hard to observe exactly the data and then, to quantify it. So it could be part of the error. Now think about that. With that, what problem could that impose? Exactly. Right? Education, think about that. Education is not like randomly assigned to each person. Right? It's not like someone is doing a randomized experiment. Oh, you are allowed to be in the school for 10 years. You are allowed to be in the school for 11 years. Let's see what will be the difference in the earning capability. It's not like that. It's what we call a choice decision. It's a choice variable. It's each individual's choice. Each individual choosing to stay in school, to receive certain level of education, stay in school for certain number of years. All right, then what affected that decision? That omitted variable, right? For example, some sort of innate ability could affect that decision. Right? It's possible that, although we don't know the exact theory, but it's possible that, let's say, people with higher, some form of the innate ability, they are willing to, take a more challenging program. They are willing to, stay in school longer. Right? Or maybe the opposite, right? If they are really like a super kind of talented, they don't need to stay in school, right? So they could actually just leave school, like Bill Gates. They could drop school. They could start their career early. But anyway, there could be some association, right? Some correlation between those missing kind of innate ability with the choice of staying in school, for a certain number of years. So in other words, this assumption may not really hold. So the utility, this error term, in our case, is very likely to be correlated with the X variable. Do you see? A person with a higher value for that X variable, a person staying in school for longer, is likely to have, higher or lower, depend on the real correlation, right? Depend is likely, let's just say the correlation is positive. So then, a person staying in school for longer is likely to have higher value for that error term. All right, let's say it's likely to have higher ability, that measure. So that the error term, right, ability is a part of the error term. So the error term, as a result, is also higher. A person staying in school, for a shorter period of time, is more likely to have a lower error term value. If that's the case, what would happen? So this assumption will be violated. This assumption says that no matter what value the X variable takes, no matter a person with higher X values, a person stay in school all the way towards that PhD, MD, degree, versus a person stay in school, just stop, the education after say high school. These two persons, the error term distribution, the expected value of this error term is the same. All right, that's what the standard linear regression is assuming. But what we just talked about, it's very likely it's not true. Right? Very likely the number of schooling, the number of years in school, number of years of education, that value is correlated, sort of says something about the potential value of this error. People receiving more education is likely to have a higher error value. People receiving less education is more likely to have a lower error value. If that's the case, think about that. What would happen? What would happen to our estimation of the return on education?
It will have wider range of, the confidence would be very low on the prediction. So if you have to look at the confidence interval of the predicted values, so it will be very wide for higher educated candidates.
Yeah, that's interesting perspective. It's a confidence level. It's about the variance, right, of this estimator. And then variance, like we said, right, variance, we don't want variance to be large, because variance large, basically, not much we can say from this particular estimator that we get. And as a result, it's hard for you to get a statistically significant result. Yeah, that's true. But let's this is more kind of like a nuanced impact. Let's focus on the first order impact. The estimated value of this coefficient before this x variable, before this education. That beta 1. This beta 1. All right, the estimated value. Think about that. How will this beta 1 be affected? Yeah, let me go show you the equation too. So let's say we want to estimate the return on education, right? So in other words, it's the marginal effect. One additional year of schooling, additional year of education, how much will that increase the expected earning? If everything works well, that will be measured by beta 1, as we talked about, right? Beta 1 directly measures those marginal effect. So that is measured by beta 1. But now that we have analyzed that this assumption, the key assumption, is likely to fail in our setting, then how will beta 1 be affected?
I think it'll be inflated upwards.
It will be overestimated. All right, think about that. What does the marginal effect, the partial effect really mean? 1 unit increase in this x variable, how much will that change to y, right? But remember, I said that there is a very important qualification condition, restriction. After that, there is another half sentence. What is that? Excellent, excellent. Everything else being equal. Holding everything else unchanged. All right, holding everything else unchanged, right? 1 additional year of schooling, how much will that increase the payoff? But now, the tricky thing is, can you really hold everything else unchanged? If this assumption fails. Let's say the error turn out is really positively correlated with the x variable's value. Then, if you increase this x variable by 1 more year, what will happen? The error turn will also increase. All right? The error turn also contributed to the earning, to the y variable. So as a result, both of them will contribute to the y variable. But if you ignore this factor, you think that the error turn doesn't change. If you still think this assumption holds, then what would you conclude? Exactly, you would attribute the contribution from the increased error turn also to the contribution from this x variable. As a result, you end up with overestimating the effect, the marginal effect of this x variable. Right, so you will conclude that, okay, 1 more year brings a lot of increase in the expected salary. But what you didn't realize is that, people staying for 1 more year, right? True, they earn, you say, a lot more. But that's because those people also have, say, higher, ability. So they choose to stay for 1 more year. But then both this additional education and also their, innate ability, both together contribute to the increase in the salary. But if you ignore that fact and that correlation between the error turn and the x variable, you would contribute all the impact on the y to this x variable. And as a result, you end up overestimating the effect of x on y. This is what we call the endogeneity issue. All right, so the endogeneity issue actually refers to the case that when the x variable, a particular x variable, is correlated with the error turn. All right, say that again. When a particular x variable is correlated with the error turn, we will call that x variable being endogenous. All right, so the idea of endogenous is it's endogenous determined. You can think of it, it's like a decision. It's not like an exogenous. So the value of that x variable is not exogenous determined. It's not like someone is randomly assigned. Or you take this x value, you take that x value. It's not like that. It's endogenously determined by each individual. So that's where the name comes from, the endogeneity. All right. Again, the endogeneity issue simply means a particular x variable is correlated with the error term. It's not independent. The error term, or in other words, the error term is correlated with some x variables. All right, error term is no longer independent from the x variables. If that's the case, we run into this endogeneity.
If the variable is negatively correlated with the error term.
It's the same. Yeah, that's a quite good question. Actually, I'm about to discuss that. Think about it. Whether you're gonna end up underestimate or overestimate this beta coefficient depends on how all those things are correlated with each other. Or actually, there are different combinations. What if the x variable itself has negative impact on y? And then what if the x variable is negatively correlated with the error term? You have different combinations that will lead to different the underestimation or the overestimation result. All right, yeah, we're going to talk about next. Okay, now, but yeah, the issue, no matter the x variable is positively correlated with the error term or negatively correlated with the error term, we all have this endogeneity issue. All right, as long as it's not independent. It's very common. It's more than common. Actually, unfortunately, it's it's almost everywhere. In all the what we call the empirical issue, you want to study, you want to look at, based on those secondary data, what we call the secondary data or observational data. This one is pretty much always present. So that's why if you are not aware of this issue, pretty much all the conclusions you get are biased. All right. Actually, that's the challenge that faces us every day. If this issue didn't exist, our life would be much easier. But unfortunately, it's just prevalent. It's just everywhere. Right. So that's why it's very important. So I feel like it's very important for me to introduce this topic. Of course, this is a very big topic. All right, how to overcome such issue, how to tease out the real causality, the causal influence. It's a big topic. You can take, not only years of study. You can take a PhD. Even after spending 5 years struggling with all those endogeneity issues, still you don't fully control them. You don't fully account for them because honestly, there's no single way that is perfect for solving this endogeneity. All right, so depending on different context, different setting, we come up with different approach. But every approach has its limitation. So there's no a single perfect solution to this problem, right? But we just do the best we can to mitigate the concerns of this potential endogeneity issue, so that we can be confident that what we get are at least the closest to the true causality, as we can. But okay, let's just so source of endogeneity. There are many different sources of endogeneity. Alright, so but for us, we're going to focus on one source that is the omitted variable, the missing variable. So some variable we do not observe, so they enter the error term, and then those variables could be potentially correlated with some observed x variables. Right, so that's actually the most common cause of endogeneity. Of course, there are other endogeneity issues like a measurement error, like a simultaneous equation. You have a supply demand, you solve them together, and then the error turning the supply function into the demand, so that everything is mixed together. So that's also possible. But yeah, those are more nuanced sources we will not cover. So we will only focus on omitted variable. Right? The cause of error turn of endogeneity is because some variables we didn't observe, like that innate ability. Right, we cannot observe, but it will affect y, and it will be correlated with this x, and then it entered error term. So as a result, this error term is now correlated with x, creating that endogeneity problem. Right, now let's analyze the direction of the bias. So where the bias comes from, why there's a bias, and what I just analyzed that intuitive reasoning. Right, we already see why it's biased, but let's formally talk about that mathematically. Let's see where the bias comes from, and then how to determine the direction of the bias. Now, let's say this is the true specification, right? Which is dependent on education and also ability. But unfortunately, we do not observe ability. So ability actually enters the error. Now, then all we observe is just the education itself. So ability enters the error term, right? This new error term called the new. So it contains this original error term plus this ability. Let's say it's like that. And then what will happen? The OLS estimation. What is the OLS estimation? If we just regress wage on education, what will happen? The OLS estimation, if you still remember, the formula is like that. The covariance, the sample covariance between x and y divided by the variance of the x variable, sample variance of the x variable. Okay? Now think about that. Covariance between x and y, right? So x is this one, but now y is this, right? Now here the x is the education, so y is equal to this, okay? So you take this out, right? So this, this one is a constant, and this one is x, right? So it's the variance of x. So then that cancels out, so you have a beta. But then you have the covariance of x and this mu, right? And divided by the variance of x. So now this is the problem. Covariance of x and mu. X and now the error term, mu. Standard assumption of linear regression is what? The error term is independent, should be independent from the x variable. So as a result, the covariance between x and the error term should be 0. Right? Should be 0, 0. Then we are good, because then the OLS estimator will be equal to the true beta 1. So the estimator is consistent, no problem. But now the question is, what if they are not independent? What if the covariance between x and mu is not equal to 0? As a result, you end up with biased estimation. Right? So if the covariance is positive, then the OLS estimator is overestimating the true beta 1 value. If it's negatively correlated, then OLS estimator would be underestimating the beta 1. You see, this is just to mathematically show you that, where this bias comes from. Alright? So as a matter of fact, what you can do is that we can write this one as this. Alright, so let me show you the more general form. What we can do is this. For the OL estimator, we can show that the OL estimator, we can run another regression of this particular endogenous x, regressing this particular missing variable on all these existing x variables. All right, so let's say this is a general specification. This is all the x variables that we observe, right? And there is one missing variable that we do not observe, one omitted variable we do not observe, so that it enters the error term. All right, so let's say, suppose we can observe this missing variable. Suppose we can run the regression of this missing variable on all of these observed x variables. Right, we run a separate regression. And then we get those coefficient delta. All right, say that again. We run that missing variable, say that in the ability, in our example, right, this missing variable. We regress that. We run the regression of that variable on all the observed x variables in our data. All right, and then we get the coefficients in front of each observed x variable. So that coefficient actually measures what? Sort of like the correlation, right, between that omitted variable and each of the observed x variable. So that is delta J. All right. So now the OLS estimator can be shown to be equal to the true beta J, right? The true beta J in front of each x variable, each observed x variable, plus this one, plus beta K times delta J. All right? Make sure this actually answers your question. How can we determine the direction of the bias? Okay? So this beta K is, again, this is the true correlation between this omitted variable and the one. Right? Let's say in our example, the omitted variable is ability, right? The y is wage. What would be the sign of beta K in our example? Hopefully it's positive, right? So people with more ability, hopefully, will end up earning more wage. Right? Sometimes it's hard to say. Maybe people, it's genius, they don't care about going to work, so they end up earning less wage. Anyway, that's a joke. So hopefully that's positive, right? So then the beta K in our example should be positive. Okay, that's the relationship between this omitted variable and the y. Right? But let's say we run, but because this is we want to determine the direction of the bias, right? So we run the regression, regress this omitted variable on all the observed x variables. So in our case, the observed variable, let's say just only one variable, just the years of education. So then we would suppose we can observe this ability value, right? We would regress this ability on this years of schooling. And then we get a coefficient. That coefficient is called delta J. So now let's say people with higher ability choose to stay in school longer. Right? Let's say that's the case. Then what would be the sign of delta J? Positive, right? So that's the positive correlation. How this omitted variable, the ability, will be correlated with the observed variable, this education. So then that delta J will be positive. So you see, beta K is positive, delta K is positive, delta J is positive. So what is the direction of bias? Overestimation. Overestimation is higher than the true beta value. All right, but let's say something changed. For example, people with higher ability choose to stay in school for a shorter period of time. Then what would change? Then that means the ability now end up being negatively correlated with the observed X variable, with this years of schooling, right? So as a result, which one will become negative? Delta J. Okay, delta J will become negative. But beta K is how this omitted variable would affect Y. So let's say still people with higher ability will earn higher salary, right? So then beta K is still positive. But if the ability is negatively correlated with the X variable, the years of schooling, then delta J would be negative. So as a result, how will our OLS estimator be biased? It will underestimate the true beta J. All right, OL estimator will be lower than beta J than the true beta J. Question?
So if I'm understanding this correctly, the OLS data is the measure of endogeneity for this coefficient beta J?
No. OLS is not a measure of endogeneity. It's the ignoring the endogeneity issue. We run that. We run the regression, without considering the potential endogeneity issue. We would end up with this estimation. But this is the true value, the true marginal effect between this X variable and Y. Okay? So, but when the endogeneity issue is really present, then how will the basic OLS estimation, ignoring the endogeneity issue, bias the value, the marginal effect of X and Y? Okay? Beyond the true marginal effect.
I'm a little confused since the variable is omitted, how can you regress it on all the other variables? We don't have that information, right?
Yeah, so that's why you will never really know how much the bias is. This is just hypothetical, right? Just to help you reasoning that what would be the direction of the bias.
But how would you find that if you don't have the data?
Yeah, you can. That's why it's theoretical. Theoretical. So it's just to show you, like mathematically show you that that's the result. That's the relation. If you knew, right, that would be the bias. That's how much the bias would be. Yes. All right. So this actually summarizes all the possibilities. Based on this relation, all you need to know is once you understand this relationship, you can easily figure out all the direction of the bias. Right? If this one is positive, that one is negative. Whether it's positive, it's overestimating or underestimation. You can easily figure out. Again, depends on two things, right? How this omitted variable affects Y, and also how this omitted variable is correlated with this endogenous X variable. All right? Then you determine the direction of underestimation or overestimation. Okay. Okay. Again, these are just like what we talk about. These are just theoretical, right? So just theoretically, if I knew the X variable, right, then how much would be the bias? But in practice, we will never observe those unobservable variables. So that's why we will not be able to quantify that. Oh, what is delta J? What is beta K? And then how much is the bias? Of course, no way we can do that. If we could do that, then that's not a problem anymore, right? So in practice, we cannot do that. So in practice, what can we do? Let's say that's all we observe: wage and education. We don't observe ability, but we suspect that ability is in play and it's correlated with education and also affecting wage. Then what can we do? We suspect that if we just run the OLS, our beta coefficient will be biased, will be overestimating the true effect, marginal effect of education on wage. Then what can we do? Well, that's the problem, right? So that's, we need to find out some solution so that we can address this potential endogeneity issue, and what we call probably tease out the true causality. Why do we call it causality? Because if we have that precise measure of the true beta value, that true beta value has the so-called causal influence. Why is it causal influence? Because it has that the everything else equal, right? Holding everything else equal. If only this variable changes, how much will y change? So in that sense, in that interpretation, it's causal. Because everything else doesn't change, right? The only thing changed is this variable, and the y changed by that much. So that much change in y is actually caused by this change in this x value. So that's why this beta, the true beta value, has the causal influence. All right, simply because it measures this, holding everything else equal. But that's exactly harder to be true. Because if the error term now is correlated with this x variable, then you won't be able to hold everything else equal. Right? So then what you measure, if epsilon error term is correlated with x, then what you measure is that if this x variable increases, how will y change? But that change in y is not solely caused by the increase in x. It's also caused by the increase in the error term associated with the increase in x. You see, so that's why if you don't have, you do not tackle this endogeneity issue, then the beta coefficient you get doesn't really measure that causal effect, the true causality. All right, so that's why causal influence is very challenging task. You need to tease out, you need to control all the potential confounding factors to allow only one variable, the variable of interest, to change, and to see how much the outcome will change. And that's the true cause. All right, so in like a business school, the research in business school, this causality, this causal influence is very important because we want to understand the underlying mechanism, right? What affects what, how much this affects the outcome. So the causality is very important, but that's exactly the hard part, right? How to tease that out. So yeah, so based on observational data, it's hard to do. So you need to think about a lot of designs, a lot of treatments, to tease out those qualities. All right, so I listed a few examples, a lot of examples that could, suffer from this potential endogeneity. It's, too easy to think of examples. For example, I want to say class participation and student performance, right? I want to collect data for each of you, how often you come to class, and eventually I look at your performance. Then I want to run regression, and I want to conclude that, okay, how helpful how helpful coming to class is, right? If I just ignore this, I just do the simple linear regression, what would I end up with? I may end up overestimating the effect of coming to class, right, on your performance. Why? Again, some missing variable, right? So students, those guys coming to class every time, probably they are, highly motivated, right? They also spend a lot of time after class, right, looking at all the book, doing exercise review, all the concept. Maybe that's the case. So as a result, they perform well in the exam. So it's not the factor of coming to class often per se that contribute to that final outstanding performance in the exam. All right, so in other words, there are some unobserved factors which will enter the error term, but those factors will be correlated with the observed x variable, which is coming to class, right? But those unobserved factors will also affect y. But if you ignore that correlation between this x and the error term, then you would overestimate the effect of coming to class on the performance, right? Endogenities. Another very classical example, it's very interesting example, is that, let's say people want to do the analysis, right? Look at the different districts within those city, metropolitan areas, and collect the data of a crime rate, and then also collect the data of a police force kind of deployment in each district. if you run the regression, want to say whether we have more police force, will that lead to lower crime rate? But if you just run the regression like that, what is the likely outcome that you see? It could be you see that with more police force,
Higher.
exactly, the crime rate is higher. Why?
Cause and effect.
Exactly, the police force employment, that's an endogenous decision. That's a choice, right? You choose to employ how much police force in what district. So it's very likely that in some district where the crime rate is high, then you deploy more police force. You see, there are some characteristics about each district, right, which is not included in your regression. That will affect the crime rate, but it also affects the police force deployment decision. So that creates endogeneity problem, making this police force deployment an endogenous variable. And then if you only regress this one on this without considering the potential correlation, then you end up, in that sense, it's what you are like underestimating the effect of police force on crime rate. All right? Yeah, another example, demand and the price. Right? So the product of, the demand of a product, the price of the product. If you collect the data, over time, right? How does the price change? How does the demand change? You regress that. Supposedly, when you increase price, the demand should reduce, right? When you decrease price, the demand should increase, right? But if you just look at, you collect the historical data, demand of price, the demand of a product, and price of the product over time. If you run regression of that, what's likely, what's the likely coefficient you get before price?
Negative.
Supposedly it should be negative, but you may end up observing positive coefficient before price. Think about why. Looks like when price is higher, demand is higher. When price is lower, demand is lower. Think about why.
Could inflation be a factor?
Actually, pricing is also an endogenous decision. You make firm price their product based on the demand, based on at least their expectation of the demand. So when the product is in high demand, they will raise their price. When the product is in low demand, they will lower their price. You see, there are other so-called demand shock hidden in the error. The demand shock affect the demand, but also affect firm's pricing decision. So as a result, if you simply ignore that the potential is you just regress this on that, you may end up totally bias the effect of price and demand. All right? And another same thing, consumer spending on promotional program sign up. If you want to say, okay, what's the effect of sign up into a certain promotional program on the consumer spending? If you just collect data like that, you just run regression, you may end up overestimating the effect of promotion sign up on the spending. Because think about it, the signing up for that decision is also endogenous. Right? Those consumers who sign up for the program are those who are more interested in buying from this company. Right? So then, there's some intrinsic interest, right? Those are the unobservable factors which enter the error term. It affects their eventual spending decision, but it will also be correlated with their decision to sign up for the program or not. So if we ignore this correlation, we would end up overestimating the effect of these promotional programs. Yeah, so like I said, so many examples. All right, so that's a very common issue. So if you want to ever tease out those causality, right, based on observational data, you have to face this problem, have to deal with this problem carefully. Okay? Otherwise, all the analysis you get, whatever regression you run, the linear regression or all those like a nonlinear regression that we talk about, all those complex nonlinear model, the Tobit model, Poisson regression, all those things, actually you will suffer from this endogenities. Okay. So the only, let me talk about that. So how to tackle this endogenities? There are a lot of different methods. But like I said, there's no single perfect solution. Even the one that we're going to introduce today, the IV, is also not a perfect solution to that. Okay, it's one possible solution, but it's not a perfect. So think about it. What is the true perfect solution to tease out, like we can say we tease out the true causality?
You can try a random control experiment.
Exactly, right? So that's the only randomized, it's a well-designed randomized control experiment. Just like what people do with this clinical trial of, like those vaccine, the COVID vaccine, for example, the clinical trial. You have to do that like the randomized, but be careful. If it's not like somebody claim I'm doing randomized experiment, the result is automatically be the valid true causality. No, depends on your design of the experiment. The design need to be valid, need to be appropriate, so that there's no potential confounding effect. So actually, it's also very hard to really design like a truly randomized experiment. Right? For example, this clinical trial, those vaccine trial, you have to, people receive the true vaccine, some people receive the placebo. Right? First of all, this assignment need to be purely random. And on the other hand, the people receiving, they cannot know. You see, they themselves cannot know, even the doctor cannot know who received the what. All right, because if the patient knows, the participant knows, then their behavior will change. Right? If they knew they got the vaccine, they will be, they will just go out and, go to all the places. So then they end up getting infected by the virus may increase. Then as a result, you may underestimate the effect of the vaccine. Right? So nobody can know. And also, you cannot have potential confounding effect. So for example, those participants cannot also be participating in other clinical trial as well. Because if they receive another, vaccine or some other treatment at the same time, then there will be like a confounding factor with that. You see, so that's very hard to design. So that's why nowadays a lot of people do those experiments, say on those like a platform, like Amazon Mechanica Turk. But that's very problematic because oftentimes those participants on those platforms, they are participating in a lot of experiments at the same time. So then it's just like they are participating in a lot of clinical trials at the same time. Then it's very hard to say that what you observe is really, the true measurement of the true effect of this particular, clinical trial, because there are potential interactions across this clinical trial. Again, so the true causality is really a challenging task to tease out. All right. So all we can do is just do our best, try all those, different methods, depending on the actual context, and then mitigate to, our best, mitigate the concern of those potential endogenities. All right. So yeah, be sure to take the right message. It's not like what we are talking about today, IV, just perfectly solve this problem. Okay. No such easy thing. All right, but still, let's just talk about this IV, this instrumental variable. So the idea of IV is that, now that we have one X variable that is endogenous, how can we, endogenous means it's correlated with the error, right? So the idea of IV is that, okay, now that it's correlated with the error, we want to try to make it uncorrelated with the error. So we want to sort of, if we can find another variable that's totally independent from the error. All right, it's totally random. It's like a randomized trial. It's totally random. And then we see how this X, we use that variable, right, to kind of extract the total randomness, total exogenous randomness from this endogenous variable to purge the endogeneity from this endogenous X variable. Then we extract the random part, the random variation inside this variable, and leave the rest. The rest is the exogenous part. Leave the rest to the error. And then we can restore an exogenous context, so that the exogenous part that we have extracted through this IV will be able to help us identify the true partial effect of this X variable. All right, so roughly that's the idea. So we want to find something that's exogenous. And then we use that to see how this endogenous variable is correlated with this purely exogenous variable. And then extract that exogenous part, so that separate out those endogenous part. The endogenous part can be now purged into the, the error. And what's left, we can be sure that it's purely exogenous. And then we sort of resolve this, eliminate this endogenities, and we can consistently estimate it. All right, so let's just formalize that to see how it works. What we can do is that, this is what we just talked about, right? What we can do is that we found one variable, an additional variable. And usually this variable is out of the picture. Ideally it's coming from nowhere. It's coming from ideally if you can find some variable coming from another planet. It's just out of the picture. Okay, so it's totally exogenous in this sense. So it has nothing to do with this error term. You see, all the problem is caused by the error term, right? So some omitted variable in the error term create a correlation with the x variable. So if I can find another variable out of the picture, z, it's totally random. So it has nothing to do with the error term. So as a result, you have no concern of endogeneity issue, for that z variable at all. Okay, so if you can find a variable like that, so z and u, the covariance, the correlation is 0. All right, z is an exogenous variable, so it has nothing to do with the error term. So the correlation is 0. If we can do so, then what we can do? We can say the covariance between z and y. Y is equal to this, right? So then the covariance between z and y can be written as this. Y is equal to this one. So then we substitute this into here. Then covariance between z and y is equal to, you see, we can do the simple expansion, right? It will be beta times covariance between z and x, and covariance between z and u. So then as a result, the beta 1 can be rewritten as this. The ratio of this covariance between z and y divided by the covariance between z and x. Right. The thing is, yeah, that's the thing, right? So this one, if this covariance between this one and the other one is 0, you can write the beta 1 as this. Right? You see, if this covariance between z and the u, this exogenous variable that we found, and the error term, the covariance, the correlation, right? The covariance is 0. So then this one is 0. So beta 1 is equal to this. As a result, so if you can find this z variable, you actually can estimate beta 1 just through this. Is that clear? So as long as the covariance between z and x is not 0, what does that mean? This exogenous variable that we found should be correlated with this endogenous x variable. All right, so that's the requirement, because if you want to divide this value into the denominator, it cannot be equal to 0. All right, we want to find a variable that's exogenous, out of picture. So it's not correlated with u, with the error term. But on the other hand, they need to be correlated with this endogenous x variable. All right, so these are the two requirements for this variable. So this variable is what we call instrumental variable. All right, if you can find a variable that is uncorrelated with this error term, which creates the problem, right? Uncorrelated with that. But at the same time, it's correlated with this endogenous x variable. If you can find such a variable, then that variable can be used as the instrumental variable. And it can help us address this endogenities. All right, once you find that variable, all you do, you can just estimate the beta 1 just by this. Right, you calculate the covariance between z, because this is a variable you observe, right? So then you observe the value of that variable for each individual record in your data. Okay, and then you can calculate the covariance between z and y, and divide it by the covariance between z and x. And that value is your estimation of beta 1. And by this formulation, it's the true value. It reflects true value of beta. All right? So then the sample, this is like a theoretical variance. Then the sample value is just like that. You estimate that it's the sample covariance between z and y, and divided by the sample covariance between z and x. And then you use that. This will be the so-called IV estimator of beta 1. All right, and this variable that you find is called IV, instrumental variable. Sometimes we simply call it instrument. All right, so this IV estimator is a consistent estimate of the true beta 1 value, as long as your assumption is right. The z is truly independent from the error. Right. But now think about that. This z, what are the requirements? I said twofold. Actually, this z is not easy to find because the requirements are twofold. One, on one hand, it has to be independent from the error term. But on the other hand, it has to be correlated with the endogenous variable, x variable. So actually, that's the hard part. Actually, if you really think, these two requirements are like contradicting each other. Right? I can easily find like a totally irrelevant variable, right? That's easy to find. Then that variable will be independent from the error term. It's totally, irrelevant in the context that you're studying, right? You can find another variable. That's no problem. But if that's the case, most likely it will also be uncorrelated with the endogenous x variable as well. Then it cannot be used as an IV. It would violate this requirement. Okay. But then you can find a variable that's closely correlated with the endogenous x variable, right? But don't forget that because this endogenous variable is correlated with the error term, what creates the endogeneity problem in the first place. So if you find a variable that's closely correlated with this x variable, and very likely it's also correlated with this error term. You see, then that would violate the first requirement. So you see, these two requirements, is sort of contradicting to each other. So that's why those IV, the instrumental variable, is not very easy to find. It's not very easy to think of. Sometimes you need to be creative to think about, what is the IV to use. Right? People often, sometimes people come up with like those nice idea of IV. They use like the weather. Weather in for example, they look at people's decision, right? So everybody's decision at a particular time, and then how will that decision, that kind of action affect the outcome. But then, they can collect, for example, weather. Weather is, random, right, supposedly. But, so then the weather will be uncorrelated with the error term. But say if this weather can affect this action variable, this endogenous x variable, then it's correlated with that x variable. And then as a result, this weather can be a good IV for the instrument. Right? But of course, this weather has to be correlated with the x variable, right? So depending on what you are studying, sometimes it's not. So that sometimes it cannot serve as a good idea. So those, it's hard to find, right? So the two requirements for instrumental variable are twofold. One is what we call the exogeneity. So the instrumental variable has to be exogenous in the sense that it cannot be correlated with the error. All right? Then, on the other hand, it has to be relevance. It has to be relevant. The relevance requirement. Relevant means that this instrumental variable has to be correlated with this endogenous x variable. These two requirements need to be satisfied at the same time in order for a variable to be a valid IV. Exogeneity and relevance. All right? Oftentimes contradict each other. So that's why it's hard to find a good IV. Later in the exam, in the homework assessment we're going to do, right? So you see, people use this, we want to do that years of schooling. This could be a potential IV, right? So whether a person lives near a four-year college or not, right? So if that's the case, it may, because that, whether the person lives near a four-year college or not could be, exogenous, that's not related to the ability of a person, right? But on the other hand, it could be potentially correlated with the years of schooling this person received. So as a result, you can satisfy these two requirements and serve as a good ID. Alright. But of course, even that, if you really think, that can also be questionable, right? Because maybe when I live to near a four-year college is not correlated with ability per se, but it could be correlated with other factors that could also be part of the error, right? Maybe those like social, financial resources, But of course, the four-year college it's not like a very prestigious college, right? It's just a regular four-year college. In that sense, it could be independent, could still be independent. It could be still sort of a randomly distributed. So yeah, probably it's fine. But again, my point is that even if you find IV, oftentimes whether it's truly exogenous, is still questionable. Okay, so that's why there's like no kind of a uniform standard to say whether this IV is really a valid IV or not, because it's really hard to say. It all depends on how you believe it's exogenous or not. Alright, so that's the requirement of IV. So what we just talked about, that's the single IV, right? So single the X variable. So in the multiple regression case, when there are multiple X variables, general case, for example, if there are more than one X variables that are endogenous, more than one X variable that is correlated with the error term, then what can we do? You need to find the same number of IVs as the number of endogenous variables. Right? For each endogenous variable, you need to find an IV. Alright, so then if you have multiple endogenous variables, then your life is even harder, because it's hard enough to find one good IV, not to mention find multiple good IVs. Alright, so if you have multiple endogenous X variable, then you need to find at least as many IVs as the number of endogenous variables. Okay, so and then you can do this basically for each IV. The condition, right? So by design, by definition, that for example, there are k endogenous X variables, so we found a k IV, okay, k IV, and then for each IV, you have this requirement. The IV is independent from the error term. This is the error term, right? Y minus all the X beta combination, so that's the error term. So that's independent from the error term. So then you have that equal to 0. So for each IV, you have one equation. Okay, and the rest, let's say only the first X variables are endogenous. So then the rest X variables originally in the model, they are exogenous. So they are good. So then for those additional X variables, they are exogenous, so they should be uncorrelated with U as well. So then you have the equations for them as well. So overall, you have the same number of equations as the number of beta coefficients. So you can solve this entire system of equations, and then that will give you the beta estimator. These are the IV estimator for those beta. Okay, based on the set of IVs that you have. Alright, this is called IV. Now, but that's a general estimation. But what we want to talk about next, what you're going to do in the homework exercise, is another approach called two-stage least square. And that's actually more commonly used approach than the general IV approach. The good thing about two-stage least square is that the general IV approach, you need to have the same number of IV and the number of exogenous X variables. Alright? But the two-stage least square allow you to have more IVs than the number of endogenous X variables. Alright, this is what we refer to as over-identification case, because you have more IVs than needed, than the minimum number needed. Actually, that's good. Alright, so actually if you can find more IVs, more valid IVs, yeah, that's good. The more the better. Alright, but usually it's hard to find, so that's why the minimum is that you need to have the same number of IVs as the number of endogenous variables. But if you can find more, that's good. And you can use this two-stage least square if you have more. The approach is like that. So let's say I have, so let's say we only have one endogenous X variable. Okay, only the X1 is endogenous. And all the other X variables, all the other independent variables in the original regression, they are all exogenous. They are all good. They are not correlated with the error term. only the first x variable is correlated with that. But now let's say I managed to find more IVs. All right, I managed to find m IVs. Again, m must be at least 1. You need to find at least 1 because you have one endogenous x variable. You need to find at least 1 IV. But you can have more. It's okay. All right, let's say I managed to have n more than 1 IV. Then what should I do? The two-stage least square. In the first stage, what do I do? I regress this endogenous x variable, right? The original endogenous variable, on all the exogenous variable. All the exogenous variable. The original exogenous variable in the original regression, plus all the IVs. All right, everybody follow me here. That's very important. Make sure you understand this two-stage least square. First stage, I regress this endogenous variable on all exogenous variables, including the original exogenous variables in the original regression and the new additional variables, the IV, the instrumental variables that I have found. Okay, you regress that, you get the coefficient, and then you get the fit the value of this. That is here in the first stage regression, the dependent variable is the original endogenous x variable. So you can get the fitted y from the first stage regression. That fitted y is the fitted value for that endogenous x variable. Now we move to the second stage. So the outcome from the first stage is just the fitted value for that x, for that endogenous x. Okay. Second stage, I go back to the original regression. But now this time, I replace the original endogenous x variable with the fitted value from the first stage regression. All right, and then run the original regression. Here, the original regression only includes the original x variables, original exogenous x variables. Here, we do not include those IVs. All right, basically the second stage is just like the original regression, but only by replacing this original endogenous x variable with the fitted value from the first stage. And then the estimated beta coefficient you get is the two-stage least square estimate. Okay, and we can show that that's equivalent to this general IV approach, and it's a consistent estimator of the true beta value. Is that clear? So make sure you understand this approach. Right? First one, we need to find some IVs, at least as many number of IVs as the number of endogenous variables. So when we only have one endogenous variable, we at least need to find one IV. Right? And then we run this two-stage least square approach. In the first stage, we regress this endogenous x on all the exogenous variables, including the original exogenous variable from the original regression, plus the instrumental variables that I found. I estimate that. And I have the fitted x value from that regression. And then in the second stage, I run the original regression, but by replacing that endogenous x variable with the fitted x variable from the first stage. And then the corresponding coefficient in front of that fitted x is the two-stage least square estimator of the original beta 1. And it should be a consistent estimator of the original beta.
So x1 is the only endogenous variable here? Or
Yes. Yes.
So you're not having multiple variables?
Yeah, right now we don't have multiple variables. But if you have multiple variables, you just run those first stage regression separately. Each variable, each endogenous variable, you regress on all of them.
So you just make the stages bigger if you have multiple endogenous variables?
Yeah, you just run separate regression, x2 on all of them, get a fitted x2. And then in the second stage, you replace x1 and x2 with their corresponding fitted value from the first stage. All right? But yeah, let's focus on the simple case, only one endogenous x. All right, now let's take a quick discussion, quick look at what exactly does this one mean? Why does this work? Basically, this exogenous variable, what do? They are exogenous, right? So basically, the fitted value, after we do, what do we do? In the first stage, we regress this endogenous X on all these exogenous X variables. What do we essentially do? The regression is like a projection, right? Project this particular X variable on this exogenous variable to use this exogenous variable to explain this particular endogenous variable. So as a result, the fitted value of this endogenous variable are only, a function of all those exogenous variables. As a result, this is the exogenous part in this original endogenous X variable. All right, because this one we can be sure by design, this X star, X hat, this fitted X must be exogenous, must be independent from all the errors. Simply because these things, they are all independent from the errors. All right, so we can be sure by design, we are sure that this one is exogenous. So that's why when in this one, in the second stage, when we do this, we can be sure that this one will be independent from the error. But what happened to the endogenous part? The original X variable is endogenous. What happened to that? That endogenous part is sort of purged from this X variable, right, through this one. So what's left, the original X1 value, the difference between original X1 value and the fitted X1 value, what's left, that is the endogenous part. But that endogenous part now is pushed into the error term in the second stage regression. But that's okay, because we are sure that all of them will be independent from this new error term. So there will be no bias in the second stage. So that's the intuition. Now, before we go, one more thing to pay attention. We talk about exogeneity, right? We said IV, there has to be two requirements. One is exogeneity, the other one is relevance. So exogeneity, we say that, it's our assumption, it's our belief, right? If it's, the IV, it should be out of the picture, so it's not, correlated with error. But how about relevance? Remember, relevance means that this IV that you found, right, at least one, right, could be multiple. So this IV you found need to be correlated with the X value. So when reflected in this two-stage least square approach, what should we check? Say this need to be correlated with X, this endogenous X. As a result, what should we see from the first stage regression? Excellent, exactly. Right, this coefficient cannot be 0. All right, has to be significantly different from 0. So what you should check is the significant level. You can look at the T statistic to make it significant. Actually, a more formal test would be based on the so-called F test. But since we didn't talk about F test, we can roughly still use the T test. All right, just look at the T test. The T statistic for this coefficient need to be very large. Actually, you need to at least make sure that it's significant at 99.9% confidence level. All right, in R, at least you need to see 3 stars for this coefficient. Then you can say that, okay, this one is significantly different from 0. So as a result, this variable is correlated with this variable, so that it satisfies the relevance requirement. All right, so that's what you need to check. All right, so in the homework, you need to do this. I asked you to do this. I already posted the video. All right, so just try to do that. And we will run the data of this return on education. Okay, you found that you use that one variable as IV, and you do this two-stage least square. Okay, I explained the video how to do the two-stage. But don't forget to check the significance, the relevance.